Yeah. So, good evening to one and all. Welcome to our first weekly discussion slash problem solving session for the Physics of Nanoscale Devices NPTEL course. My name is Jyotishwaran. I am a PhD student from the ECE Department of Indian Institute of Technology, Roorkee. So, I am a teaching assistant for this course. So, I shall be conducting these sessions every week, same time, for 2 hours. So the structure of our sessions will be that I'll try to solve some problems and cover the concepts that were covered in the preceding week so that it will be of some help in your solving the assignments that are due next week. In addition to that, I shall also be looking at the questions that are posted on the course forum and I will answer them here. I shall also be answering those questions on the forum as well. I shall be answering the questions here for the benefit of the people who are not looking at the forums and who would like to, have their doubts cleared. Yeah, just 1 second. So that will be the basic overview of our sessions. In addition to that, any questions that you might have, you're more than welcome to ask during the session. You can either post your questions in the chat or you can unmute and ask your questions directly to me. In fact, I would prefer that because talking one way for 2 hours is kind of, it feels weird. So please feel free to interrupt, ask any questions, any feedback that you'd like to give. So with that, I will start today's session proper. So I hope my slides are visible. Someone can confirm that in the chat. Okay, yeah, I mean, I got the screen sharing notification, so I guess the slides are visible. If there are any issues, please let me know. So today, what we shall be doing is in this course for the first 2 weeks, week 1 and week 2 assignments are both due on the 7th of February, which is roughly which is the week after next. So in today's session, I shall be focusing on the contents of week 1, which is essentially the overview of the course and the basics of quantum mechanics. And in the next Saturday's session, I shall be looking at the one-dimensional solids, chronic penny model, and all those things, which are more relevant for the assignment of the second week. So this week, I shall not be going into that. I will be focusing mainly on the contents from week 1. So moving on. So these are the topics that we shall be looking at. So first, of course, we shall be looking at the motivation for our course. So course overview. Here what we shall be looking at are the motivations as to why we are studying the things that we are studying. And after that, of course, in this we shall mention that basics of quantum mechanics is necessary. So we'll be looking at the Schrödinger wave equation and solution to this equation under certain particular conditions. They will be explicitly solved in this session. And we shall also be looking at the Heisenberg uncertainty principle. Though this will not be applicable directly in week 1, an important application of this will show up in the subsequent weeks. Then using everything that we have covered here, we shall look at the particle in a 1D potential well. Again, we'll solve and get the explicit expressions that are required for this problem, and we shall conclude today's discussion with Bloch's theorem. So the overview, like why are we even studying this course? Why are we here? Why do we consider learning about nanoscale devices? It is essentially a market motivated area. Like, of course, there are domains of theoretical interest in constructing smaller and smaller devices, but the motivation for constructing smaller and smaller devices comes from the fact that we have an ever-increasing demand for computational power. So That implies in a given chip or a device of a certain size, I will need more and more fundamental computational units to increase the computational power of a given device. So that implies we will have more transistors per unit area. Now, to make the transistors, to increase the number of transistors that can be packed into a given unit area or unit volume, what we'll have to do is reduce the dimensions of the transistors themselves. That implies we will have to construct short channel transistors. So when we consider short channel devices where the channel length is of the order of nanometers, the classical treatment is no longer valid. Essentially what this means is the theory of electronics that we have, where we consider p-type, n-type materials and then consider their junctions and the properties and behavior of those things in order to study the behavior of devices such as diodes and transistors, is no longer valid. And because of that, a new theory of mesoscopic / microscopic conduction is required. So that will be the central focus of the first half of this course, and using that we shall set up a bottom-up approach towards the study of the device. What do we mean by bottom-up approach? Bottom-up approach implies we will, let me change the color here. Yes, so bottom-up approach means we will start from the electrons. Like first we shall study how the electrons behave in these systems, and from there we shall move to the behavior of the devices. Typically, or rather traditionally, when electronic devices were constructed, these were the first transistors were constructed in the late 30s and early 40s. So this was the time when quantum mechanics as a discipline itself was growing. So people did not have much understanding of what electrons behaved like in solid materials. So the classical approach for device construction is a top-down approach where the device is constructed first and then the behavior is studied. Here we shall look at the bottom-up approach where we will study the fundamental properties of the charge carriers, and we will then try to construct devices where desirable properties of these charge carriers are manifest. So that is our aim in this course. And of course, when we move to the regime of nanoscale devices, quantum mechanical effects become dominant. So in order to understand the quantum mechanical effects, we will have to understand the basics of quantum mechanics. So that brings us to the contents of week 1. Just 1 second. Yes. So, yes. The extent to which, now this is not going to be a first principles introduction of quantum mechanics, because of course that is not the central focus of this course. However, I do have some experience and I've learned some quantum mechanics over the years. So in case anybody has any questions, you are free to ask them here or post them on the forum. I shall answer them wherever the question is posed. But for the purposes of this course, we shall start our quantum mechanics discussion from the one-dimensional Schrödinger wave equation, which is given by this form. It is a linear partial differential equation of the wave function of a particle. So what are the properties of a wave function? So what are the properties of a wave function? So wave function, first and foremost, it has to be finite. So a wave function can never take infinite values. Second, a wave function by and large is expected to be continuous. There are no exceptions, not generally. A wave function should always be continuous. Like why? We shall see that in a minute. Continue. Oops, wrong spelling. Where is the eraser? Yes. Oops. Yes. And in general, it is expected that the first derivative is also continuous. This is not always true, but in general, most examples that we shall consider, this rule is applicable, is continuous. And so these are the three properties it is supposed to obey. In general, psi of x for a one-dimensional system is a function that goes from the set of real numbers to the space of complex numbers. So this is a complex valued function. Complex valued function. And according to the Born interpretation of quantum mechanics, this quantity, the absolute value squared psi of x, mod squared psi of x, I shall be calling it as, is the probability density of the particle. So what does this mean? Mod squared psi of x gives me the probability of the particle being found, that is probability of, I'll use a different bracket for this, probability that particle is between x and x plus dx. So essentially, let me make this parenthesis bigger, parenthesis, the curly braces. So yeah, I seem to have run out of writing space. It's understood. So this quantity here, psi of x squared dx, is this. It is the probability of finding the particle between x and x plus dx. So if we want to find the probability of the particle being present in a certain region, we shall integrate this quantity over that region. We shall do this pretty soon. We shall do this as one of our examples in today's session. So first and foremost, we shall consider the free particle solution. So this kind of gives us an idea of what kind of a function this wave function will be. So what do we mean when we say we are considering the free particle solution? We mean that v of x is equal to 0 for all x. So this is a one-dimensional system for x from minus infinity to infinity, minus infinity less than x, less than infinity, v of x is 0, 0 everywhere. So now what will happen to this Schrodinger wave equation in that case? What happens is we shall have minus h bar squared upon 2m. Since it is only one variable, this need not be a partial derivative, but still for the sake of propriety, I am writing it as a partial derivative, because when we consider multidimensional systems, the partial derivatives are necessary. So psi of x will be equal to e times psi of x. So this is the differential equation that we will have to solve. Now the solution to this equation can be obtained as follows. Let me just insert a new slide. Yes. So yeah. So the equation in the previous slide can now be written as by dou x squared psi of x is equal to minus 2me upon h bar squared. times psi of x. Now this is of the form of a standard differential equation. Let me get rid of these boxes. Yeah. So here I can take k is equal to square root of 2me upon h bar squared. The square root is also for the denominator. That implies this equation will become dou squared upon dou x squared psi of x is equal to minus k squared psi of x. So this is the standard form, and this has solutions of the form is equal to a e to the power I kx plus b e to the power minus I kx. So in this case, the solutions are given by these exponential functions where the exponent is an imaginary quantity. It is understood in general that energy E is greater than 0, greater than equal to 0 in general. Again, there are exceptions to this rule. We shall look at them later, but for now we will consider the cases where E is greater than 0. So these are our general solutions. Of course, it can be seen from here that e to the power I kx is a complex valued function. So this can be written as cos kx plus I sin kx. So these are oscillatory solutions, which is why the original Schrödinger equation was called the Schrödinger wave equation. So this is the free particle solution. So this is the free particle solution. We shall be using this later on. And this value is k is defined as this. K is known in quantum mechanics as the wave number, and also in like general theory of waves, k is known as the wave number. So this will play an important role. Now from here we can see that, let me just drag this whole thing above. Yes. Yeah. So since this is of this form, we can say that E is h squared k squared upon 2m. So h bar squared k squared upon 2m. I'm just taking the original approximation that I had here and I'm just rewriting E in terms of k. So given a wave function that is defined by e to the power ikx and e to the power plus kx, we can say that the energy will correspond to this value. Additionally, we know from classical mechanics that E is equal to p squared upon 2m. So this is the relation between energy and momentum in the non-relativistic limit. So from this we can say that the momentum is h bar k. Like these two expressions, p squared is replaced by h bar square k square. So from that we can say that the momentum of a particle is h bar k. So this is a semi-classical way of arriving at the quantum mechanical expression for the momentum. There is also a purely quantum mechanical way of deriving it. Of course, that is not of our direct concern, so we shall not be doing it. So now we shall consider a second problem to this. Get rid of these things. If you have any doubts with what I'm doing, please either ask them in chat or you can directly unmute and ask me. Ask me straight away. So the second problem that we shall consider is v of x is equal to v0. Again, this is for all x. Minus infinity, less than x, less than infinity. So in this case, what happens is we will have to write the term that we got rid of in our Schrodinger equation in this slide over here. The v of x term will now appear. So here the equation is given by, again, minus h bar squared upon 2m squared psi of x plus v0 or v0 psi of x, which is equal to e psi of x. Now this can be written as minus h squared upon 2m is equal to e minus v0 psi of x. So now this equation again comes back to our standard form, where I can say that dou squared psi of x upon dou x squared is equal to, let me use a different symbol here, let me say it is beta, is how shall I write this? So yeah, I'll leave it as positive. So I'll say this is equal to beta squared psi of x, where beta is this quantity over here. It is square root of v0 minus e by, oh sorry, forgot the mass factor. It is square root of 2m into v0 minus e by h bar squared. So this is beta. So in this case, psi of x will have a general solution of the form. Yeah, I need not use a and b again. I had already used it for the previous case. So I shall call it c e to the power beta x plus d e to the power minus beta x. So this equation where beta has this value. However, now we have two cases. We have the case where now v0 minus e can be either positive or negative. So we shall have to consider both these cases. So first let us consider, let me just duplicate this slide here and erase all of these things. take this. Over here. Take this over here. So first case we have V minus V naught minus E is greater than 0. This implies E is, let me say, greater than or equal to 0. This implies E is less than or equal to V naught. So here the energy of our particle is lesser than the potential level. So it is having an energy that is below the potential level. So in this case, what will happen is our solution remains the same. However, what we should remember is that the wave function, I'll go back here to look at the properties of the wave function, it has to be finite. So in this case, if I consider the cases where beta is positive, then one of these functions must be dropped depending on the sign of x. Because if x is positive, then as x becomes larger and larger and larger, e to the power beta x will tend to infinity. If x is negative, as I tend to minus infinity, e to the power minus beta x will tend to infinity. Therefore, we will have to take either this term over here or this term over here, depending on which side of which part of the x-axis we are in, the positive axis or the negative axis. So what we have to remember here is, from this we have the first point, either e to the power beta x or e to the power minus beta x, and of course whichever, like if I'm in the positive side, I will take e to the power minus beta x. That implies the wave function will always have a decaying trend. This means, oh, not trend, apologies. A decaying trend. This implies as x tends to infinity, psi of x tends to 0. So now what does this imply? This means, now remember, going back to our original definitions, this is the probability density of finding the particle. So if the wave function psi of x tends to 0, that implies that the probability of finding the particle there also tends to 0. This means that the particle that we are considering is now not found everywhere. Whereas in this case, I should have explained this before, but let me do that now. In this case, if I take the absolute value of these two quantities, it will depend on the values of A and B, but the absolute value of this quantity over here, so let me write it here, mod e to the power ikx is equal to 1 for any real values of k and x. As long as k and x are real, e to the power ikx is going to be a phase factor. So people who are familiar with alternating current circuits or the theory of complex numbers will know that this is a unit complex number. It lies on the unit circle in the complex plane. So the absolute value of this wave function will depend on the values of A and B, and it will be 0 if and only if both A and B are 0. But if A and B are both 0, then the wave function itself will become 0. So this quantity in general is either 0 everywhere on x, everywhere in the x-axis, or 0 at only particular points or particular regions. Whereas here what happens is, after a certain limit, the value of psi of x will tend to 0. So this means our particle has a high probability of being found in a finite region in space. So this is what is considered as a bound state. So whenever we are considering at bound state solutions, we establish a potential and we say that our quantum particle is bound in that potential. So what does that imply in terms of energies? It implies exactly this. Like whatever the value of our potential, the energy of the particle has to be less than or equal to the potential. So yeah. And then there is the final case, V0 minus E is less than or equal to 0. This of course implies that E is, okay, since I put equal to in the previous case, I will not put an equal to here. I will say it is strictly less than 0. This implies E is greater than V0. This will imply that, very directly, this will imply that beta is now imaginary. Because square root of a negative number will be iota times square root of the magnitude of that negative number. So beta becomes imaginary. This implies for E greater than V0, the solution is the same, because what will happen if I substitute this by an imaginary number? I will get a solution that is similar to the free particle solution. So in this case, the solution is the same as the free particle solution. So this is a very important feature that one finds in quantum mechanics. Of course, this can be observed in, this is also observed in the case of classical mechanics, but here this has further implications. So first and foremost, we have a situation where depending on the energy of the particle, it is behaving either as a bound particle or a free particle. So the boundedness or the freeness of a particle is defined by the binding energy or the potential energy in which the particle is present. And the other consequence here is that if it is a bounded, as a direct consequence of this, the free particle wave function is defined on all values of x from minus infinity to infinity, and the bound state wave function is defined only in a limited region in space, essentially as x tends to infinity. In fact, I can even generalize this by saying x tends to plus or minus infinity, psi of x will tend to 0 in this case. Whereas here, in general, psi of x does not tend to 0, it just keeps oscillating. So this situation is also not very realistic, because ideally speaking, a given particle cannot travel to infinite lengths. Typically, particles are confined in a finite volume. So more or less the solutions that we shall be looking at will be of the first form. So we shall be looking at that pretty soon, how to arrive at such solutions. But when we are considering two extremes of the Schrödinger wave equation, where we consider a totally zero potential and a constant potential everywhere in space, we get these two kinds of solutions to the equation. So this is the solution to the Schrödinger equation. So we'll move on to the next topic, which is the uncertainty principle. Oh, did I write energy momentum? Yeah, let me correct that right away. It is not energy momentum, it is position momentum. Yes. So the position momentum uncertainty relation is given by this relation. Essentially the x component, the uncertainty in the x component of momentum and the uncertainty in the x coordinate of the position is less than or equal to h bar by 2. This quantity in some texts is written as h upon 4 pi because of course h bar is h by 2 pi. So this result is due to Werner Heisenberg, one of the founding fathers of quantum mechanics, and this is a very important tool when we are studying quantum phenomena. Another related uncertainty relation which we shall be looking at pretty soon in like maybe week 3 or week 4 is the energy time uncertainty relation, where I will say delta E times delta T is again less than or equal to h bar by 2. So this is also another uncertainty relation, of course, but right now we are considering this case, the position momentum uncertainty relation. Now what does this mean? So let us look at that by a direct example. So we are considering a particle that is confined in a one-dimensional space of 5 nanometers. So what we are asked to do is to estimate the minimum energy that can be possessed by this particle. What is the lowest possible energy this particle can have? So how do we solve that? What we know is the particle is confined in a 5 nanometer region. This implies that delta A or delta X has a maximum value of, oh sorry, not greater than or equal to, it's the other way around. It is less than equal to A. So let me consider the greatest possible value of A. Why am I considering the greatest possible value of A? That will give me the lowest uncertainty in momentum, and that is what I shall use to estimate the lowest possible energy, the minimum energy that can be possessed by such an electron. So let me consider the case where delta X is equal to A. So delta X equal to A implies delta Px will be equal to, or rather will be less than or equal to, according to the uncertainty relation, it shall be less than or equal to h bar upon 2a. Now this is the, like this essentially gives us the minimum momentum that the particle can possess. So that is always going to be less than or equal to this quantity over here. So what is the lowest possible energy that this particle can possess? It will just be the, like this can be taken as Px. Now why is that the case? Because the delta X and delta Px that are given here, these can in a sense be interpreted as the standard deviation in the quantities, in the respective quantities, the errors. Or in an alternate, another way of looking at it will be to consider the fluctuations. Essentially, what this relation means, like the most straightforward implication is that Px and X cannot simultaneously, like this is another way the uncertainty relation is stated, have a fixed value. So if X is fixed, Px cannot take a definite value. In fact, if delta X tends to 0, delta Px will tend to infinity. Similarly, if delta Px tends to 0, delta X will tend to infinity. Both of these are unrealistic cases. So usually what happens is delta X will also have a finite value and delta Px will also have a finite value. What this means is that a quantum particle is actually never truly at rest. Just 1 second, let me have a drink of water. So in that sense, as I was saying, Px and X cannot simultaneously have a fixed value. And in the cases where they are fixed, the fluctuations, where one is fixed, the fluctuation of the other tends to infinity. That is also not a very practical case. So usually both of these have a small finite value. Now, if that is the case, then I can take the maximum deviation, maximum allowed deviation of the momentum to be the value of the momentum itself. So this implies this is equal to upon 2a. This is P. Now, as discussed before, therefore E is given by P squared upon 2n. So that will give us a minimum energy, E min of h bar squared upon 4 ma squared. So this is the minimum possible energy the particle can have if it is confined in a space of length a. So in the case where a is equal to, so here I am saying a is equal to 5 nanometers in this problem. So that will be in E min is, I'm not going to do the exact calculation, I will just use the order of magnitude and say what range the energies will be in. So the mass of the electron is around 10 to the power minus 30 kilograms, and here I have 5 nanometers, so that is going to be 25 into 10 to the power minus 18 meters in SI units. So 25 into 4 is 100, so that is another 10 to the power 2, so that will like, the denominator has a total power of 10 to the power minus 48, 2 of which will be removed by this factor. So this is approximately equal to h bar squared upon 10 to the power minus 46, and h bar is approximately, let me write that in blue to just clarify here. Where shall I write it? I'll write it here. H bar is approximately 1 into 10 to the power minus 34 in SI units. Okay, so the unit here is Joule second, or the unit of angular momentum. So since this is 1 into 10 to the power minus 34, the square of that will be approximately equal to the square of that will be approximately equal to 10 to the power minus 68. So here in the denominator I'll have 10 to the power minus 46. So this gives me something to the tune of 10 to the power minus, did I miss something here? No, I didn't. Yeah, 10 to the power minus 22. So now this is of the order of milli electron volt. So this tells us what is happening in the system. So what this means is that if I am trying to confine an electron in a volume, in a space of say 5 nanometers, then this is the lowest possible energy that the electron can possess. It cannot have an energy that is lower than this. So the moment I try to confine electrons in a tight space, remember I have not mentioned any potential energy here. I am not giving any potential to the, applying any potential to the system. By just confining the electron in a limited region in space, the electron acquires a non-zero value of energy. Now, this quantity is very small, yes, I agree, but it is not zero. This is definitely not zero. In fact, this is of the order of milli electron volts. And electron volt is approximately 10 to the power 19 joules. So this is 1/1000th of an electron volt. So this implies in quantum mechanics, in a realistic situation where I confine my particle in a limited region of space, it is always going to have an energy directly by virtue of its confinement. So this notion is what is called, so the reason why we did all of this is to introduce ourselves to this notion of the so-called 0-point energy. Meaning, this energy to the system will always be present. This is not something that is related to the motion of the electron. This is not something that is related to an applied potential. This is not something that is related to the temperature. If I cut off all of these parameters and if I still confine my electron in a finite region, this much energy will always be present. So that is where we get this notion of 0-point energy, which implies when we consider, like, this 5 nanometer is a very important figure, because this is roughly to the order in which we are constructing devices these days. So nowadays the channel lengths are around either 9 millimeters or 7 millimeters in our, I think they are either 10, 9 or 7 millimeters in FinFET designs. So this is a very representative figure in that sense. So in our modern devices, what essentially happens is the electrons that are present in the channel can never have a zero energy. They will always have a non-zero energy, which implies they will also have an intrinsic sense of motion, because when P is not zero, that implies delta P is also not zero. If delta P is not zero, then delta X is also not zero. So depending on how small my channel will have to be, I will also have to set my expectations on the average energy of the electron. So the scale of my device, the size of my device will also dictate the energy scaling of my system. And similarly, there is a connection between the time and the energy levels. So that will be seen during your lectures. And of course, when that is covered, I shall come back to this expression again, and we shall work out a few more problems. So this comes to, this expression is what is important for us right now, that E min, for this particular case, we have derived it to be h square upon 4ma. So moving on, we are at the particle in a 1D potential well. So over here, what is a 1D potential well? Like, this is the mathematical representation of the potential in a, yeah, so beforehand I apologize, I'm not very good at drawing things. So in case if there are any inaccuracies, kindly put up with me. Yeah, I should use the lines on the slides, and even then I cannot follow it. There it goes. Yeah, so this will be kind of an ongoing thing. So whenever we are looking at our weekly discussions, I shall spend somewhat unnecessarily long time in drawing things. So what is happening here is, this is x equal to 0, this is my x-axis, and this is the potential. So I have a wall here and another wall over here. So this is x equal to a. So in this region, v is equal to 0. In both of these regions, v is infinity. So that is what I've written over here in this expression. Now this is what is known as a 1D potential well. Now what happens to a particle that is placed in such a well? So first we shall consider here the potential can have two values, so we will have to solve the Schrödinger equation in two limits. So first and foremost, we shall consider the case where v of x is equal to infinity. The reason I am considering this first is I have very little space here, and this is the smaller of the two examples. So I shall take that over here. So in this case, what happens is I will have minus, again we shall be solving the Schrodinger wave equation, upon x squared psi of x. What I will do is I will write this as v psi of x is equal to e psi of x, and I will take the limit v tending to infinity. So this is in the limit v tending to infinity. Now what we can do is we can divide both sides of this equation by v, and what we will find is that 1 over v over here, so this implies minus h bar squared upon 2m into 1 over v to x squared psi of x plus psi of x equal to e upon v psi of x. So in the limit v tending to infinity, what happens is psi of x equal to 0 is the only acceptable solution, because this term will vanish, so will this term as v tends to infinity. So what we will have is psi of x on the left hand side, and on the right hand side there will be nothing. So this implies psi of x is equal to 0. Therefore, the solution to this problem, let me write it in black. So right off the bat, we know that psi of x is equal to 0 here and psi of x is equal to 0 here. Again, according to the interpretation, what does this mean? It means that the particle has a 0 probability of being present in this region and a 0 probability of being present in this region. Therefore, the particle is now confined in this area. This is another way of creating a bound system. Like essentially what we have is, for energy values, for all energy values, all available, all permissible energy values, I shall come to the notion of what permissible energy values are. The particle cannot leave this well. So this 1D potential well is also alternatively known as an infinite well, or it's also called particle in a 1D box. Essentially, there is a box and my particle is inside the box. It can never come out of the box. The box is permanently closed. That is the understanding here. This is not a physically real situation. However, it has conceptual relevance. Understanding the solution to this problem will help us understand a great deal of things as we progress in the course. Yeah. So, coming back. So, we know that psi of x is 0 in a certain region. Now, what about v of x is equal to 0? In the limit where v of x is equal to 0, we already have solved the Schrodinger equation for that. Therefore, we know that, like, this is the equation that we will have to solve. So this is why I had solved the free particle solution beforehand, so that we don't have to spend too much time over here. Psi of x is equal to e psi of x. So this implies psi of x is equal to a e to the power ikx plus b e to the power minus ikx. For 0 less than or equal to x less than or equal to a. This needs to be like clearly understood, because v of x is 0 only in this x range. Therefore, psi of x can have this form only in this range. Everywhere else, psi of x is 0, as we have seen before. So now, how to get the exact values of a and b? We'll have to use what are known as the boundary conditions. Now, what are the boundary conditions? The boundary conditions are that psi of x at x equal to, the wave function has to be continuous. So how do we derive our boundary conditions? We go all the way back here, and so in the case of our bound solutions, we have seen how to use the finiteness. Now in the case of our particle in the 1D box, we shall look at how to see how the continuity of the wave function comes into role. So sorry, comes to play a role. It doesn't come into role. So yeah. So I know that psi of 0. Oh, oops. I know that psi of 0 is equal to 0 and psi of a is equal to 0. So if psi of 0 is equal to 0, I will just set x equal to 0 here. These two quantities will become 1. This implies a plus b is equal to 0, which implies a equal to minus b. So first let us consider the implications of this before going on to psi of a equal to 0. So what does this mean? What this means is, if a equal to minus b, then psi of x is equal to a into e to the power ikx minus e to the power minus ikx. That is equal to twice iota a sin kx. All we have to do is consider, which is the expression? Yeah, this expression over here. So this thing that we have derived over here, I'll just take this, take the difference between k equal to plus k and minus k. Cos of minus kx is the same as cos kx, but sin minus kx will acquire a minus sign. So the difference of that I will get to be sin kx. Sorry. Yes. Now, what about this factor of iota? Like, what is it going to give me? Iota can be neglected. So, yes. So, this quantity over here can be neglected. Now, why can it be neglected? The reason is that because this is a constant, like norm of I or mod of I is equal to 1. This is a constant unit complex number. So this quantity is in no way going to alter the probability density. So if I consider a wave function that is 2 iota a sin kx or 2a sin kx, the probability density functions developed from them is one and the same. This implies these two wave functions describe the same kind of probability distribution. Therefore, we can neglect it. So this quantity is not equal to, but it is equivalent to 2a sin kx. Now, we know that psi of a, small a, is also equal to 0. This implies 2a sin ka is equal to 0. Now a of course cannot be 0 because then the wave function will be 0 everywhere, which implies the particle has 0 probability of being found everywhere. So a definitely should not be 0. The only case where sin ka is equal to 0 is if k is equal to n pi, where n is, we can consider the case where n is equal to 1, 2, 3. N is a natural number. Because if n equal to 0, then again this will be the 0 function. And that cannot be allowed because again the wave function will be 0, no particle will exist. So n equal to 0 is not permitted. You can ask what happens if I take negative values of n. Then I will get an overall minus sign over here, which can again be neglected by the same logic because mod of -1 is 1. So the probability density functions defined by that wave function will be the same for the case where I consider plus n. Because of that, I am considering only the positive values. These will give me distinct wave functions. So first we know that k is equal to, sorry, n pi by a. Yeah, I forgot the a factor. Yes, n pi by a, where n is equal to these things. So therefore, psi of a is equal to, in fact, what I can say is I can take this 2a and replace it by some a prime because it is again a constant. And I will say this is sine n pi upon a. So finally we have to determine what the value of a is. Now how do we determine the value of a? Again, we go back to our definition or fundamental properties of the wave function, where this is the probability density of finding the particle. Now we know for a fact that our particle is completely confined in this region. It is completely confined between 0 and a, which implies integral 0 to a, not psi of a. Yeah, I should write this correctly. Made a few mistakes here. Yes, psi of x is equal to n pi by a times x. Yes. So psi of x squared dx should be equal to 1, because this is the total region in which the particle can be present, and the probability, sum of all possible cases, should be 1. So performing this integral, I think this has also been covered in the slides, so I shall not do this integral in detail. I'll just write this integral. You are encouraged to work it out and find it out. So 0 to a squared sine squared n pi, oh sorry, n pi by, God, apologies, yeah, n pi upon a times x dx is equal to 1. So what you can do is you can write this as 1 minus 1 minus cos 2 kx by 2, and then take the factors out, and from that what we will get is a is equal to square root of 2 upon a. And this is kind of to be expected, because this is dx. This thing has dimensions of length. Therefore, mod squared psi x should have dimensions of inverse of length, because this quantity in here, sine of n pi a by x, is a dimensionless quantity. So even by dimensional analysis, you can say that this would be something of the form 1 over square root of length. And of course, it turns out to be not 1 over square root of length, it is a square root of 2 over a. Therefore, we have the final wave function, which is of the form, okay, we have someone joining us an hour after the fact. Just 1 second, let me let them in. So yeah, going back to our slides. So what shall I do? Yeah, in fact, I'll go back one slide and I will just write it over here itself. I will say psi of x for this is again defined piecewise. Oh, sorry. It is square root of yes, I have a better idea. I can do this 2 over a whole power half. Yeah, this is easier for me. Sine n pi upon a into x for x, let me write it on the line below, and 0 here. So this is 0 less than or equal to x less than or equal to a, and it is 0 otherwise. So this is the complete solution for the particle in a 1D box. Now of course we can now take this form of our wave function and substitute it in the Schrödinger equation to get the energy for the particle. That is the question here. Compare the ground state energy to the estimate from the previous problem. So what does the ground state energy come up to? The ground state energy will be, or rather first let us get the general expression of energy, and from there we shall look at the ground state energy. Oh, did I duplicate it? No, I just need a new slide. Yeah. So now we have E psi of x is equal to minus h squared upon 2m dou squared upon dou x squared psi of x. Now from this we can see that any constant that is multiplying the wave function does not matter. So the square root of 2 by a factor will vanish from both sides. This implies E times, and the second derivative of sine kx will be, so I will just directly write that here. So d squared, since there is only x, partial derivatives are equivalent to standard derivatives or proper derivatives. Sine kx is minus k squared sine kx. So essentially this will be multiplied by minus k squared, therefore this will give me the expression. Oh yeah, forgot a squared here, upon 2m into n pi a squared. So this is the expression for the energy. We can further write this as n squared h bar squared pi squared. This is typically the standard formula that is written upon 2m a squared, and for the ground state is, of course, here we have to say that n is equal to 1, 2, 3 and so on. So ground state is the lowest possible energy for the system. So that corresponds to the case where n equal to 1. This implies E ground state, let me call it GS, is equal to h bar squared pi squared upon 2ma squared. So the minimum, oh yeah, pi squared, yes. The minimum energy that we had estimated in our previous question over here was this quantity. It is h bar squared by 4ma squared. Now I have h bar by ma squared and I have a quantity pi squared by 2 multiplying with it. It can be seen clearly that pi squared will be like greater than 9, it is 3.14 squared. So this quantity is definitely greater than 1 by 4, which implies this ground state energy is definitely greater than the E min that we had derived for A. So the derivation that we did using the Schrödinger wave equation is in agreement with the estimate that we made using the Heisenberg uncertainty principle. It is an agreement. Essentially, this is the lowest possible energy, which was to the order of milli electron volts. But of course, in this case, we see that it is around 10 times more than that, which is kind of what happens. So what we will have is around like 1/10 of an electron volt is typically what the energy values we will observe in a short channel device where the length is in the order of nanometers. So this exercise was to show that. And with that, we come to the final exercise, or rather the final problem that we shall be considering, which is the Bloch's theorem. Now, I shall not, of course, we shall not be looking at the derivation of the Bloch's theorem. That is a proper quantum mechanics problem. What we shall simply consider here is the following potential. For people who have seen the lectures for week 2, this part will be very familiar. But for people who have not seen that, this is kind of a prelude to what is going to happen in the next week. So let us consider a potential of the form, essentially a periodic potential, where why am I looking around? I'm sorry. Yeah. So what I shall say is L is equal to A plus B, and what I will say is this: V of x is defined as follows. V of x is V0 for 0 less than x less than or equal to A, and 0 for A less than or equal to x. Should I have that? Yeah, sure, by all means. Less than or equal to A plus B. So what is happening here is, and of course, V of x is equal to V of x plus n. So, yeah. So what will this potential look like? It is a periodic potential, and let me say V naught is greater than 0, just for the sake of consideration. So it is going to be some positive value V naught. Of course, this is the x-axis, this is the potential axis, so it is going to be, yes, and then it is going to be 0 until this point. So this is A, this is A plus B, and so my potential will look something like this. Once again, it will go up and it will stay like this, this. So this is a periodic square potential like this. Again, for people familiar with electronics, this looks like a square pulse train. So this is a periodic square potential. And the solution to the Schrödinger equation for such a potential, of course this goes both this way and this way, the solution to such a potential well is obtained using the Bloch's theorem, where the general form of the solution takes this kind. So it is e to the power ikx times u of x, where u of x is a periodic function. So right away, what one can say is this implies magnitude mod psi of x is equal to e to the power ikx, as long as k is real and x is real, for any value of k and x is unimodular. It's a unit magnitude complex number. Therefore, this is equal to mod ux. Therefore, as far as the probability distribution of the electron is concerned, that is going to be periodic, because if these two are equal, then the square of these two quantities are also equal. This implies, since u of x is periodic, the probability density function is also now a periodic function. However, the wave function itself is not periodic. So, what Bloch's theorem effectively tells us is the probability density is periodic, but wave function need not be periodic. Of course, if k equal to 0, the whole thing becomes, wave function itself becomes periodic. Need not be periodic. So the function that obeys these two conditions can be defined as such. So we will start from a wave function that looks like this. However, what we can do is we can solve the Schrodinger's equation piecewise to solve this problem properly. So that will be the last slide I shall add for today's discussion. So essentially, solving the Schrodinger's equation for this problem can be split into two parts. So first we shall consider the case where 0 less than, so again, to solve this equation, all I have to do is solve it from 0 to a plus b. I don't have to solve it for anything beyond that, because to go from this region to the next region, all I have to do is multiply it by e to the power ikx. Okay, so yes, so for the first case where 0 less than x less than or equal to a, we have v of x is equal to v naught. This implies in this region psi of x will have a solution of the form given over here. It will be of this form. So c e to the power beta x plus d e to the power minus beta x, where beta is 2m. No, I should not write it as e minus v naught, because in my convention I have chosen to represent it as v naught minus e. H squared whole power half. And for a less than x less than or equal to b, we have v of x is equal to 0. So in this case, of course, we know the solution is psi of x is a e to the power I kx plus b e to the power minus ikx. Now, how do we find the values of a, b, c and d? We go back and apply these two conditions. So this is where the first derivative is continuous. The property will be applied, because first we will say that the wave function should be continuous. Therefore, we will have, there are two boundaries. So, yes. Yes. So there are, went back to the first slide. So in this potential, if I consider the fundamental period, like the region from 0 to a plus b, there are two boundaries. So what we can say is the wave function from this region should be continuous over here, and from this region should be continuous over here. Additionally, the derivative of the wave function should also be continuous in these two regions. So that together will give us the necessary wave function with appropriate values of A and B. I shall not be solving this because this is what is going to be done in the week 2 lectures, which should be available to you by now. So boundary conditions, let me just mention it here. Conditions are as follows: psi of x 0 plus is equal to psi of x 0 minus. 0 plus and 0 minus are the left and right neighborhoods of the point 0, and similarly psi of x L plus is equal to psi of x L minus. And similarly, we will have two more conditions, which is d by dx psi of x 0 plus is equal to d by dx of psi of x 0 minus, and analogously we will have a condition for this, and like essentially the equivalent condition. So there are 4 unknowns A, B, C, D. Using these we shall get those 4 values of A, B, C and D to define our wave function. So that will give us the periodic component of our wave function. In addition to that, we will need to multiply it by e to the power ikx. Now the nature of the value of k will be derived during the course of your lectures. Of course, when I revisit this topic next week, I shall be starting from here. So the aim of this session was to work out some basic problems, which we have done, and give an introduction to how calculations and derivations are done in quantum mechanics. So that part has also been covered, and I've kind of established a lead-in from basic quantum mechanics to this potential, which shall be dealt in a model that is called, like this shall be covered in the topic, that is called the Kronig-Penney model, named after the two people who first solved this, or in short it is called the KP model. So this will be the central focus of next week's lectures, and of course as a result it will also be the central focus of next week's assignments. So we shall have a more detailed discussion of this and some problems in this next week. So with this I end the problem solving part. So as mentioned at the beginning of the session, I shall answer any questions that you might have. So if you have any questions from week 1 or even week 2 for that matter, feel free to type them out in the chat, and or you can also ask me directly. In the meantime, like if you have a question, you can raise your hand. In the meantime, there was one question from the course discussion forum, so I shall answer that. Of course, I will not, I mean, unless and until you are asking me a question here, I will not be naming the people who are asking the question, just because, you know, I don't want to take names very often. So you are actually free to ask any kind of question. There are no bad questions. All questions are valid. And in any question that you ask, as long as it's a proper question, I am obligated to answer. So the one question that I had found last week from the forums was essentially, why does the number of collisions, that is electron-electron or electron-ion or electron-nucleus, reduce as
channel length comes down to nanometers. So this was a question that was asked. So the answer to this can be given in two parts. So first and foremost, as we have discussed today, quantum particles. So like this comes from the Heisenberg uncertainty relation part, which is over here. So it is this. This implies that they cannot have a fixed value of momentum and position. So quantum particles always fluctuate. So I cannot definitely say where a quantum particle is or how it is moving. I cannot definitely say that. It is kind of, distributed in a region. So since there are fluctuations, instead of fluctuate, I will say fluctuations. Even if my system has only one electron, I cannot deterministically track its trajectory. So what we will do is, we will have to deal with this situation in a probabilistic manner. So in this case, what we will do is, given a sample, let us say I have a sample of length L. So this is the sample of length L. And I have one electron over here. Now my question is, how many other electrons or nuclei or ions is this thing going to collide with? I cannot definitely say because I don't know where it is. I don't know how it is moving. What I can say, however, is in a given duration, how many collisions will happen. I can give a probability of a collision occurring. So that can be defined. Alternatively, what I can do is, I can say what is the distance that the electron will travel before having from one collision to another. Essentially, what I will say is, on an average, again, this is not saying that when I am traveling this distance, no collision occurs. In general, the average number of collisions for this distance is 1. That's what it means. Okay, so on an average, every electron will encounter at least one other electron or a nucleus if it has traveled this distance. Let me call this distance lambda. So this is lambda. So if my sample is of length L, then the number of collisions that my electron, the average number of collisions, can be written as lambda upon L. Oh, sorry. It should be the other way around. Apologies. It should be L upon lambda. So when this L is very large compared to this quantity lambda here, then I can say that the electron is experiencing a lot of collisions. It is not allowed to travel freely, or rather, I shouldn't say freely. It is, it just implies that it encounters a lot of collisions. However, as L becomes smaller and smaller and smaller, the average number of collisions becomes lesser and lesser and lesser. So consider the case when L is approximately equal to lambda, then this quantity will tend to 1, like average number of collisions will slowly become 1. And in the limit where L is less than lambda, the average number of collisions will actually go less than 1, which implies on an average, like this is the average of a quantity that can only take values 0, 1 and like this can only take whole number values. So if the average goes to less than 1, this implies on an average the electrons do not undergo any collisions. This quantity lambda is the mean free path of an electron. there is also a classical statistical definition of the mean free path, which again is equivalent to what I defined in terms of quantum fluctuations. Classically, we have a large number of particles, so it is impossible to track each and every one of them. So again, we have to come into a statistical picture, and after that, everything else that I've defined is more or less the same. So this lambda is usually of the order of a few nanometers for an electron. Therefore, when we look at nanometer channels, our L is comparable to the mean free path. This is why we no longer have to consider electron-electron collision or electron-nucleus collision in channels that are the nanometer dimensions. Of course, if it goes even like below nanometers, it goes into the sub-nanometer regime where we essentially have only 1 or 2 atoms in the channel, then we will have to do a complete full quantum mechanical treatment. So if you remember in your slides, there would have been like 3 pictures depicting the motion of an electron. Like there will be one case where the electron will move like this, like this, like this. It will essentially undergo a lot of collisions back and forth, and it will keep moving like this. So this is when L is much larger than lambda, because a lot of collisions are occurring. And you will have a case where more or less I can treat the electron as a particle and I will say it is traveling in a straight line without any collisions. This is the case where L is approximately equal to lambda. And then you have the third case where you have, like here, these lines denote wave fronts. So these are wave fronts. So here I have the case where L is less than lambda. So this is the classical limit. This is the semi-classical, where I can still treat the electron as a particle, and more precisely this is called the ballistic limit, and this is the full-on quantum limit. So our primary concern is actually in the ballistic limit. Like this will be the majority of the cases that we are considering. 1 or 2 cases we shall look at the quantum aspects as well, but primarily our focus will be the ballistic limit of electron transport, and this is the theory of transport that we shall be developing in the coming weeks. So, but in order to do that, we will have to understand the basics of quantum mechanics. We'll also have to understand a little bit of the Kronig-Penney model, and after that, slowly we shall move on to establish the theory of conduction for this limit where L is approximately lambda. So that is what I had mentioned in the new theory of mesoscopic / microscopic conduction is required. So this is for the ballistic limit. So yeah, I can see that many of you have already left the session. That is, I mean, absolutely fine. You guys can join and leave as you please. So yeah, with that I come to the end of my presentations. So yeah, what was I saying? Yes. So that was the one question that I encountered. If you have any questions, like I still have around 15 minutes in the session. I can kind of end it early today. I mean, I'm not obligated to stretch this to all 2 hours. So if you have any questions, you are free to ask. Okay. So yeah, so there is the h by 4 pi comment which I addressed. H by 2 pi. Okay, so this was a question that was asked. Unfortunately, I had missed it. So it would also be beneficial if you guys can raise your hand, because then I will get an audio notification. Because typically for chat messages, I don't seem to be able to get a sound ping. So for people who are watching the recording, please raise your hand while you're asking questions here, or you can simply just unmute and talk. Like, I will welcome that, because this frankly is very exhausting for me. So if somebody else talks for even 1 minute, I will take that break to, you know, breathe for a while. So yeah, so this is exactly what I've taken. So this question from Rajesh Reddy is, that's essentially what I've done. Like, I've taken the value of delta x, and then I've just taken the limiting case, set it to be equal, and solved the problem. So that is what was done in that thing. So whatever was suggested here is what happened there. Again, like, apologies for this session. The chat messages were, I was not able to read them during the session. Next time onwards, I'll keep the chat window open separately so that I can view the two together. So yeah, that is done. Divya has asked for the pattern for the final exam. It is going to be similar to your assignments. It will be objective questions. It will be based on all the topics that were covered. You may have questions that have one or more than one answer correct. I think that is also the case for your assignments. And there will be negative marking. So that is that. The exam for this course is in the same pattern as the assignments. I see no further questions. So I think with that, I will end today's session. I thank everyone who, yes, of course, negative marking is there. I mean, it's an objective exam. If there is no negative marking, then people will start statistically cracking the exam. So yeah, and during my problem solving sessions, I'm not allowed to exactly solve the assignment questions. So for any who are watching the recording of this or anything else, if you think why I've written some functions or some things in a certain form and not in another form, well, the reason is obvious. It's because it has something to do with the assignment. However, there are enough hints. Like, if you go through whatever is discussed here, more or less you should be able to answer. No, assignment, there is no negative marking. Assignment, you can answer all the questions as there are. Like, I mean, if I can see here, let me see this. So over here, oh, so the rules are not mentioned here. Okay. So yeah, there is no negative marking for the assignments. The assignments you can attempt to your heart's content. However, in the examination, there will be negative marking. Okay, so that is all. I thank you all for attending today's session. We'll meet again next week, same time. Thank you.